Started.
We present Songs Like Me, our final project for CS4641.
So the status quo right now is that Spotify ultimately recommends songs based on user behavior and listening history. And the general problem with this is that Spotify is ultimately designed for existing music collection in the industry out there right now. However, it's not adapting to the music industry that is up and coming. So our affected audience is ultimately this group of up and coming artists who are trying to get their music noticed on the platform. So the general idea behind this is that we are trying to make a song recommendation system that ultimately uses quantifiable features instead of user history to recommend songs to the user base. So this kind of brings us to our general solution, and that means that we're going to use the Spotify Audio Features API and kind of combine the data that we collect from there with unsupervised learning and supervised learning, and ultimately create an adaptive approach for the song recommendation system that works for new music.
So the first step in this approach is to take existing songs and extract audio features. Then we form clusters based on these features. Now we have a new artist that just published a new song. We fit this new song to a cluster that we already have, and then we recommend the new songs from this cluster to the user.
We accumulated a bunch of Spotify playlists to encompass many different genres, and we are able to directly extract quantifiable features from these songs using the Spotify API. So upon doing so, we can see that there's a whole list of features, but we decided to limit it to just about 12 of them. And these 12 are the danceability, energy, the ones up here, because these are quantifiable features, and these are able to work with the clustering algorithms that we wanted to implement. And to visualize this data, we implemented principal component analysis onto this. So we conducted PCA of 2 dimensions so we can generate 2D plots that show our data. That green plot, each one of those green dots is a song from one of these playlists. So if you wanted to count, it's probably impossible, but you find there's 2,572 these green dots, and each of these represents a song. So using these songs, or using honestly data points, we are able to then cluster them. First implementation of clustering we used is k-means. So we used k-means, and we saw that maybe 5 clusters based on the elbow method would be a good minute, or a good number of clusters, and it looks good. We ran k-means, we had 5 clusters. The problem here is it doesn't suit what we want our algorithms to do. If we take a look at this green plot, for example, we see that there's an outlier in the top left, and that's being clustered as the same green plots that are towards the center. So the intra-cluster variation is very high. Not good. We look along this line that separates the green and the yellow points. These green points are right next to these yellow points. Their distance is very close, meaning they're similar feature-wise. However, they're in 2 different clusters. They're not going to be recommended, even though they're very similar. This is also not good. Hence, we used different algorithms to combat this.
Another issue when looking at this data set is that there is varying density across the data. K-means does not take this into account. We can see there's a low density region over here and kind of along the perimeter, whereas we have the high density region on the inside. We think that incorporating this will greatly improve our results, and so we utilize the only unsupervised machine learning technique that we learned in class that takes into account density, dbScan. With dbScan, we can only look at one density regime at a time, and so we chose to look at the high density region because we think that variations within the high density will lead to more specific song groupings rather than these very large groupings seen with k-means low density classifying scheme. We can see the results of our dbScan on the entire data set in this figure here. A result of looking in the high density regime is that all the low density data points are classified as outliers, This is very bad for a data efficiency standpoint. But when we look at the clusters that we have made, they seem to have achieved what we were aiming for. We see that low intra-cluster distance and that higher inter-cluster distance. But again, since this is so inefficient, we wanted to explore another technique. That technique is called optics. It is essentially the same as dbScan, except it relaxes the epsilon parameter, which is used to classify what a neighboring point is and what isn't. It's the range. So then this enables dbScan to be applied to or extended to high and low density region data. We can see the results of this algorithm down here. Again, we see those low density points and those clusters and those high density clusters. This helps us better capture the entire music space that we're looking at rather than just the high density region. And we can see all the points together without the outliers here. We think that these clusters will be the best clusters of those looked at so far for matching songs in the results section of our report.